Hello and welcome to Lecture 4, the course ECE 257A at the UCSB. This is the last chapter in part 1 of the textbook. Part 1 is basically introductory material and tools that we need throughout the course. And the title of chapter 4 is State Space Modeling. Another class of modeling techniques beyond the combinational modeling that we studied in the previous chapter or lecture. So state space modeling, I will define what it means, how it's used, and so on. Okay, so this is where we are in the textbook, last chapter of part 1. Starting next time, we will enter into these various levels of the 7-level model of dependability, dealing with defects, faults, errors, malfunctions, degradations, and failures. So we will devote 2 lectures to each of these parts, unlike the first part where we devoted 4 lectures, 1 per chapter. Okay, so what is state space modeling? With respect to the availability of resources and computational capabilities, a system can be viewed as being in one of several possible states. And you can basically define as many states as you want as they serve your purpose. So you can do very fine distinctions between different states, or you can lump states together into these blobs, big blobs. So here on the diagram, you see very coarse representation of the system as being in one of 4 states. I just call them arbitrarily the great state, the good state, the so-so state, and the lousy state. Okay, it's not a very technical example, but you get the picture. The system, from our viewpoint, from how it serves the purpose for which it was designed and built, can be doing great, can be doing a good job, can be in the so-so state, or in the lousy. Lousy you can view sort of as the failed state. And then let's say the probabilities assigned to these states are as shown in the red numbers on the diagram. 86% probability that the system is in the great state, 8% probability that it's in the good state. These are somehow derived, okay? I'm not yet telling you how to derive those, but suppose we know those probabilities. 4% in the so-so state, and 2% in the lousy state. And of course, these numbers must add up to 1. So its system is 1 and only one of these states at any given time. So the system moves from one state to another as resource availability and computational power change due to various events. So the system may be operating in the great state, something happens, and it may go to the so-so state. Now, in the context of this course, some failure occurs, for example, something fails. Or it can go into the good state, which is a less serious failure. Okay, well, when it's running in the good state, it can go into the lousy state, or it can go back. So some other failure occurs and the system gets even worse, or some improvement occurs, like something is repaired or replaced, and it goes from good back to great. and so on and so forth. These transitions generally have probabilities associated with them, and therefore with some probability when the system is in the good state, it goes into the lousy state, or it goes into the great state. I haven't put the transition into the so-so state, but there could have been a transition from good to so-so as well. So these, where I put these transitions depend on how I manage the system and how it operates. So in this case, you see that from great to lousy, there's no transition from great to lousy, because I've designed the system so that when something fails, it goes to one of these partially operational states rather than go directly to the failed state. So these are functions of the design of the system. So state space modeling entails quantifying transition probabilities. So these transitions have some probabilities. So in the discrete case, they have probabilities. In the continuous time model, they have rates. The rate means at what rate the system goes from the so-so state to good state. The rate can be, for example, twice per month. That's the rate. So if I run the system for a long time, twice per month, I would experience this transition from so-so to good. Okay, so transitions are quantified either by probabilities in the discrete case or by rates in the continuous time model. Some of these states are more desirable than others. Okay, so we are interested in finding out the probabilities of the system being in this most desirable state, in this somewhat less desirable state, and so on, because those help us assess the usefulness of the system in a probabilistic sense. Okay, the starting point for our discussion is the model known as Markov chains, sometimes called Markov models. So what is a Markov chain or Markov model? Here I've shown a four-state system. This is actually the same system in terms of transitions. Oops. In terms of transitions and states as the previous slide, except that I've numbered the states 0, 1, 2, 3. So from the numbers, it's not immediately obvious, which are the desirable states, which are the undesirable states. It doesn't matter. In Markov model, we don't make judgment. They're just a bunch of states. There are a bunch of probabilities associated with transition. So this is a discrete time Markov model. So this says over a unit of time. So you can imagine that this system is running. There's a clock. And on every clock pulse, every clock cycle, there's a 30% probability that the system transitions, if it's in state 0, transitions to state 2. There's a 40% probability that it goes to state 1. So 0.3 plus 0.4 is 0.7. That means with 30% probability, those are all the transitions out of state 0. So that means with 30% probability the system remains in state 0. These are self-loops that are not shown in this diagram to avoid clutter, okay? Because their probabilities can be derived from the other transitions, okay? So the row 1 of this matrix, this is known the Markov transition matrix. So each row corresponds to a state, 0, 1, 2, 3. And each column corresponds to a state, 0, 1, 2, 3. And this 0.3 is probability of transition from state 0 to state 0. That's the self-loop that I talked about. State 0 to state 1, that's 0.4. State 0 to state 2, that's 0.3. And state 0 to state 3, that's 0 because there's no transition. Similarly, state 1 to state 0, 0.5. State 1 to state 1, 0.4, that's the self loop. State 1 to state 2, there's no transition there, so that's 0. And state 1 to state 3, that's 0.1. Okay, so Markov matrix is a square matrix with number of rows and columns equal to the number of states in the Markov model. The entries in each row add up to 1. Okay, that's a key feature of a Markov matrix. In the Markov matrix, every row, entries in every row add up to 1. That means the state must do something, either stay in the current state or move to some other state. Okay, now one nice feature of this transition matrix M is that if you know the current state of the system, so the current state of the system is basically a vector. If the vector is 1, 0, 0, 0 in this example, that means we know for sure the system is in state 0, and it's not in state 1 or state 2 or state 3. Okay, this next one says the system is equally likely to be in states 0 and 1, but it's definitely not in states 2 and 3. And this one means the system is equally likely to be in any of its 4 states. We don't know. We have absolutely no information about what it is. So the state of the system is defined by a vector whose elements add up to 1, just like a row of a Markov matrix. If one element is 1, the others are 0, that's a certainty about the state of the system. Otherwise, we have partial information or total lack of information in this last case. Okay, so one of the nice properties of this Markov matrix is that if you take the state of the system at time t and multiply, so that's a vector, multiplied by matrix M, you get the state of the system at time t plus 1. Remember, this is discrete time. So in 1 unit of time, the system goes from state S of t to state S of t plus 1 that is determined by multiplying S of t by m. So here's an example. Suppose the current state of the system is 0.5, this one up here, meaning that it is in state 0 or 1 with equal probabilities, and it's not in state 2 or 3. Multiplied by that matrix, normal vector by matrix multiplication, and you get this vector that says in the next time step, the system is in state 0 with probability 0.4, state 1 with probability 0.4, state 2 with probability 0.15, state 3 with probability 0.05, 5%. Okay? If I continue this one more step, so now take the new state of the system and multiply it again by transition matrix, I get this. So after 2 time steps, the system will be in state 0 with 34% probability, and state 1 with 36.5% probability, and so on. So after h time steps, the state of the system at time t plus h is derived from its state at time t by multiplying it by the h power of this transition matrix. Now, any power of this transition matrix, we can prove that is also a Markov matrix. In other words, if you take a Markov matrix and raise it to any arbitrary power, the result will be a Markov matrix. Okay, there is something called stochastic sequential machines. In fact, this is how I was introduced to Markov models. As my master's thesis, I was working on these. I was interested in sequential machines and in particular in stochastic sequential machines. A sequential machine receives inputs and transitions between its states according to some state table. So the state table tells us if the state is currently A and input x equal to 0 is received, what the next state will be. If the input x equal 1 is received, what the next state, and these are deterministic, meaning it will go into those states for sure, according to that state table of the machine. Now, stochastic sequential machines have probabilistic behavior, and they are defined by as many Markov transition matrices as there are possible inputs. So suppose I have just one input, j, which is binary. It can assume the value 0 or the value 1. This is the transition matrix if the input happens to be 0. This is a different Markov matrix that applies when the input is equal to 1. So basically, I have to put on these arrows now, as we do with sequential machines. For input 0, what happens? This is for input 0. And for input 1, this transition from 0 to 2, instead of being 0.3, will be 0.1. Okay, I haven't drawn that. So this is just the transitions for input being 0. We have a similar diagram, or we can merge the two diagrams, just labeling these arrows as we do in sequential machines, input slash probability of that transition. So it will be, in this example, 0 slash 0.3, meaning that if input is 0, this transition occurs with probability 0.3, and 1 slash 0.1. So a Markov chain is basically an autonomous sequential machine. It doesn't have any inputs, just moves between states on its own. So it's a special case of a stochastic sequential machine. There are many applications for Markov chains. I have drawn some diagrams outlining 3 such applications. There are many more. So let me just describe one of these examples up here. This is a Markov model for a programmer's activity. The problem is formulated, the program is written, the program is compiled, the program is tested. Okay, then it is debugged. We go back to compile and iterate in this cycle until we are satisfied with the test. Then we run the program. After we run, if it runs okay, we may want to optimize it and then compile again after optimization, run again. We may go in this cycle many times. Or from the run state, we can go back to debug. Something happens here. From test, we can go directly to out. In other words, we are satisfied and we don't do anything more. Okay, now the transitions in this particular diagram, this happens to be an old UCSB project. So on this transition, you see probability 1 and a latency 268 seconds. That's sort of the expected or average amount of time spent in programming before we go to compile. These are apparently simple programs that take a few minutes to write. For compile, we always go to test, so this probability is 1 after, say, 49 seconds on average. After test, with probability 0.713, we go to debug. With probability 0.237, we go back to program. With probability 0.048, we go to run. So these parameters, of course, somebody had spent time and collected data to assign values to these parameters. And then now, once we have the model and its transition probabilities and latencies, we can evaluate how much time a programmer spends programming. How often are we in this state? How much time is spent compiling? How much time is spent debugging, and so on? Okay, so it models programmer behavior and where she or he spends time in this particular space of activities. Now, let me give you a Markov model example for a computer system. This is basically what we are interested in this course. So here I have 8 states for this computer system. And this is a simplified model of a 3-processor parallel system in which the states correspond to a subset of the processors being functional. So state 111 means all 3 processors are functional. State 110 means the first 2 processors are functional, operating. The third one has failed, and so on. And of course, the worst state here is when all 3 processors have failed and the system cannot do anything. It doesn't have any processing resources to get work done. And then transitions between these states, basically there's a transition from 111 to 110. This transition is when this third processor fails. So the state goes from 1 in this position to 0. And let's say that has a rate lambda. So we are now switching to continuous time model. Rate lambda, for example, lambda can be 10 to the minus 8 per hour, meaning that if we operate the system for 1 hour, there's a 10 to the minus 8 probability, a small probability, that this transition is taken. Okay, it doesn't mean this transition is taken at the end of the hour. It can be taken at any time. It's continuous time. But the average rate of this transition being taken is 10 to the minus 8 per hour. There's also the possibility of repair. So the repair rate, let's say, is mu. That's again a random variable because some repairs take little time, others take a lot more time. So we model that by defining a repair rate. So for example, the repair rate can be 4 per hour. In other words, on average, 4 of these failures can fix per hour. In other words, it takes an average 15 minutes to repair the system. Okay, so this rate mu is typically much larger than lambda, so the system is much more likely to be in this state. If it just goes out of that state, it will likely go back to that state quickly and does not spend much time in this failed state, partially failed state. Okay, similarly, we can assign transitions to the other ones. So if all the 3 processors are identical, then I can say, okay, this is also lambda, this is also mu, and so on. In this case, processor 3 has already failed. Processor 2 also fails when we go into this state. So this is still lambda. Okay. So now we may decide that we really do not need 8 states for this particular system to model this system. If these 3 states are really the same when one processor has failed and the processors are identical, we may not care whether it's the third one that's failed or the second one or the first one. So we merge these states into a single state, and we name the states according to how many processors are operational, 3 or 2 or 1 or none, 0. Okay, now the transition from this state to this composite state has 3 times the rate because processor 3 can fail, processor 2 can fail, processor 1 can fail. So we label this transition with 3 lambda. We label this transition with 2 lambda because there are 2 processors, each of which can fail. And we label this one with lambda. The reverse transitions, notice that I've labeled all of them with mu. This is the case when we have just one repair facility or one repair person. So that even if 3 processors have failed, we can't fix all 3 together. We have to focus on one of them. So at the rate mu, we repair 1 and get here. At the rate mu, we repair 1 and get here. Of course, this is an assumption, okay? We could make the assumption that we have, let's say, 3 repair facilities or 3 repair people, in which case I would put 3 mu here because the fixing will be at the rate 3 times as much when there are 3 failed. And I can put 2 mu here, and I can put mu here because there's just one processor that does fail. So these are parts of the setting up of the model, okay? And you need some knowledge of the conditions and situations to be able to set up your model correctly. If having one processor is not acceptable for us, we may also decide to lump these 2 states together and say the system has failed. So the system has failed if it has 1 or fewer processors operating. Again, this is context dependent, depends on what we plan to do with this system. Okay, it may be that 1 processor is still okay, the system is at least partially operational, or we may decide to lump these 2 together into a failed state. So setting up Markov model for a system is non-trivial. You have to think about a lot of issues about what states to use, what rates to assign to transitions, and so on. Okay, so let's start setting up Markov models for systems, beginning with simple ones, and then going to more complex ones gradually. So here is a 2-state system, which has the 2 states are up, or state 1, and down, or state 0. And the failure rate of the system is lambda. So at the rate lambda, the system goes from the up state to the down state. Notice there's no transition out of this 0 state. Such a state is sometimes called an absorbing state. An absorbing state is a state where the system goes into it, there's no way to come out. Okay? So for such a non-repairable system, if you operate the system long enough, the system will end up here. So you start the system in this state, it's operational. At some point, it may be in the near future, it can be, in the distant future, at some point it will eventually fail, and the system will go here, and then it's done. You can't do anything with it at that point. So this is known as an absorbing state, where there's no transition out of the state. Okay, in order to evaluate this, so this is a very simple Markov model with 2 states. I leave it up to you to write the Markov transition matrix. In order to solve this and find out the probabilities of being in the 2 states, each of the 2 states, we set up a differential equation. And of course, we know that P1 plus P0 is equal to 1. The system is either in this state or in this state. So this gives us one equation. And the first one is also one equation. We have two equations and two unknowns that we can solve. So what is this first equation? This one says that the rate of change of the probability of being in state 1. So this is the derivative, p prime 1. P1 is the probability of being in state 1. P prime 1 is the derivative, the rate of change of that, is proportional to probability of being in state 1, P1. And the negative sign is basically means the probability is reduced over time. And lambda is the rate at which we leave that state. Okay, so the rate of change, the probability being state 1 is equal to minus lambda times the probability of being in state 1. Now this is a very simple first order differential equation, and its solution is P1 equal to e to the minus lambda t. This is the exponential reliability that we obtained previously. And then P0, of course, is 1 minus P1. And if I plot P1 over time, this is what I get. P1 is equal to 1. When t is equal to 0, P1 is equal to 1. As t goes to infinity, P1 tends to 0. And of course, P0 changes in the inverse direction. It starts with 0, and then eventually it goes to 1. Okay, so this is basically known as the transient behavior of the system. It's transient because, it changes time. As this system does not have any meaningful steady state, because steady state over the long run, the system is here in state 0. Therefore, in steady state, P1 is equal to 0, P0 is equal to 1. So that's not very interesting. But the transient variation of probability is given by this equation. So probability of being in state 1 is reliability. So this is reliability. Probability of being in state 0 is unreliability. Okay? So this is the simplest case. Very easy to solve the equations. Here's a more complex example. Modeling a k out of n non-repairable system. So we start with n functional units, and then one of them fails. That can occur at the rate n lambda, and then we have n minus 1 functional units. Then one of these n minus 1 fails at this rate until we get down to k. Okay, the system is still functional as long as at least k out of n units are operational. But upon the next failure, which occurs at the rate k lambda, we go into k minus 1 functional states. And from that point on, we can have more failed units. All of these are essentially, from the viewpoint of this k out of n non-repairable system, these are failures. So we can lump those together. So this system has states n, n minus 1, n minus 2, k, and then f for failure. Again, f is an absorbing state. So in the long run, the system is sure to end up in this f state. So steady state probabilities are probability of f equal to 1, and probability of all of these other states being 0 in steady state or long term. However, again, we can set up differential equations. So p prime n, rate of change here, is proportional to Pn, and negative sign is again because that's reduced. We leave that state. There's no way to enter that state. There's no repair. We always leave that state at the rate n lambda. So the rate of change is proportional to n lambda, and proportional to the probability of being there in the first place. Okay, so this leads, solving that first differential equation gives Pn equal to e to the minus n lambda t, probability of being in this state. Then it becomes more interesting as we go to the other state. In this state, n minus 1, we have both departure transitions and arrival transitions. So the rate of change of probability of state n minus 1 is positively correlated with Pn, because we can go from Pn to here, so that adds to the probability of being here, and this one subtracts from the probability of being here. So n lambda Pn minus n minus 1 lambda Pn minus 1. Okay, we already determined Pn. We plug it in here and solve this equation, differential equation, and get this answer. And similarly, we continue until pk, the rate of change of pk is dependent on pk plus 1 and pk. So the negative term is for pk, that's departure. The positive term is pk plus 1. And finally, we have this equation that the sum of probabilities of being in these various states and the failure state should be equal to 1. So that gives us the probability of being in the failure state as 1 minus summation of all those that we found up there. Okay, so this is modeling k out of n systems using a Markov chain. Again, the Markov chain is absorbing, it is an absorbing state, so eventually the system will end up in this failure state. But meanwhile, during smaller time periods, when t is smaller, its behavior is governed by these equations. Okay, now it gets more interesting when we have repair. This is a two-state, again, the simplest repairable system has two states. The start state, where the system is up, and the down. And this is basically the model. Up is state 1, down is state 0. A failure rate lambda takes us from 1 to 0. Repair rate mu takes us from 0 to 1. Okay, now it makes sense to do steady state analysis. So with these models that don't have an absorbing state, because if you have an absorbing state, then all the probabilities in the long run are zeros, and the probability of the absorbing state is 1. In this case, it makes sense to talk about steady state. The system moves back and forth between state 1 and 0. Sometimes is in state 1, a fraction of the time is in state 1, a fraction of the time in state 0. So to find the steady state probabilities, we set up what are known as balance equations. So this is P1 plus P0 equal to 1, that we know. This is a balance equation set up for state 1. We say basically minus lambda times P1, that's the basically rate of departure from state 1, plus mu times P0 plus mu, that's the rate of entry into the state 1. If you are in the steady state condition, these two should be equal. In other words, lambda P1 should equal to mu P0, and therefore we solve these two equations and get P1 equal to mu over lambda plus mu, and P0 is lambda over lambda plus mu. I mentioned previously that mu is typically a much larger number than lambda. So mu divided by lambda plus mu is very close to 1. And lambda divided by lambda plus mu is very close to 0. And of course, you see that the sum of these two is equal to 1. Okay, so this is basically how the probability of being in state 1 changes. It begins with 1. At the outset is 1. Then it drops and drops and drops until it gets to the steady state, which is this value. Similarly, the probability of being in state 0, initially it's 0. Okay, and then it increases until it gets to 1 minus this value. So it increases until it gets to 1 minus this value. Okay. So this curve that you see here, which includes the transient behavior as well as the steady state, is has this equation. So probability of being in state 1 as a function of time, and we will derive this later, okay? For now, let's accept it. Mu over lambda plus mu plus lambda over lambda plus mu e to the power minus lambda plus mu times t. Let's test this. If t is equal to 0, then this term becomes 1. So we have mu over lambda plus mu plus lambda over lambda plus mu, which is 1. So at the beginning, it's 1. If t is infinity, steady state, then this term becomes 0, because there's a negative sign there. This term becomes 0, and the steady state availability becomes mu over lambda plus mu, as we obtained with that simple analysis. Okay, so I'll show you by the end of the lecture how to derive this transient behavior of the system, not just the steady state. Steady state is always easy because you just set balance equations. Okay, so here is a more complicated system that has a good state, two fail state, type 1 and type 2. Perhaps this is, say, a safe fail state. This is an unsafe. So that's why we are distinguishing them, because the consequences of this failure are different from the consequences of this type of failure. Okay, so this is the model. 2 is the operational state. 1 maybe is the failed safe state. 0 is the failed unsafe state. Okay, as an example, it can be any two states. Then we have transition rates. So from this state, there's a rate lambda 1. So when the system fails, at the rate lambda 1, it fails to this state. At the rate lambda 0, it fails to this state. And let's say the sum of these two partial failure rates is lambda. In other words, the total failure rate of the system is lambda. A fraction of those failures take us to state 1. A fraction take us to state 0. And then repair, let's say, is at the rate mu, regardless of which state we are in. So we are now interested to find out the steady state probabilities of this system being state 2, state 1, state 0. Again, we have this equation, P2 plus P1 plus P0 equal to 1. The sum of probabilities of the three states is equal to 1. And these are two balance equations for state 2 and state 1. For state 2, we say minus lambda P2. So these are the exit. Minus lambda 1 and minus lambda 0 together, those are lambda. Minus lambda P2 plus mu times P1 plus mu times P0. Okay, so that should be 0 in steady state. For state 1, minus mu P1, that's a departure transition, plus lambda 1 P2 should equal to 0. Okay, you may be curious, what happens if I set up the balance equation for state 0. For state 0, I will get minus mu p0, that's the departure transit, minus p0, plus lambda 0 p2 is equal to 0. Turns out that that equation will not be independent, so I couldn't set up just the 3 balance equations and solve them, because those are not independent equations. They don't give you unique answers. That's why I am forced to use this equation involving the sum of probabilities being 1. So I could have set the balance equations just for these two and not for state 2. That would still have worked. So these two balance equations plus this third equation. So the answers here are P2 is mu over lambda plus mu, P1 and P0. And this is the situation here. P2 starts with 1, probability 1 at the beginning, and it drops to a steady state value. P0 and P1 start with 0, and they rise to their respective steady state values. Okay, so as you see, the models are getting more and more complicated, but once you know how to handle these balance equations, no matter how complex the model, you can set them up and solve them. So here's another model of a fail-soft system. You can visualize this as a system having two processors, and if one of them fails, we go into this state, and if that's the second one also fails, we go into this state. And the transition rate is lambda 2 here and lambda 1 here. Of course, if these two processors are identical, you could have set 2 lambda here and just lambda here, but I'm setting up the model to be more general so that this transition can be anything depending on the context where we are using this model. So there's a different transition rate between states 2 and 1, and between states 1 and 0. And again, for generality, the repair rate I'm taking mu1 between these two and mu2 between these two. Once I solve the model with these general parameters, I can, of course, consider special cases where this is 2 lambda, this is lambda, this is mu, this is mu. These two are equal. Okay, again, I set up the balance equations. I won't go through them. And this sum of probabilities being equal to 1. I solve them, and these are the equations where delta is this rather messy expression. I've written it up there so that I don't have to repeat it in each of these equations. So P2 is delta, which is given by that equation. P1 is delta times the ratio lambda 2 over mu2. And P0 is delta times lambda 1, lambda 2 divided by mu1, mu2. Okay, now I forgot to mention in the previous model, here when we had two failed state, we can do safety evaluation. So if being in this state, fail type 1 has some consequence, let's say some dollar cost for us, and being in this state has some dollar cost, then the risk will be probability of being in this state times its corresponding dollar cost, plus the probability of being in this state times its corresponding dollar cost. So this allows us to do safety evaluation. We did reliability evaluation before. This is now something that allows us to do performability evaluation. So let's say the system has some level of performance state 2, some perhaps smaller level of performance in state 1, and let's say 0 performance in state 0. Or more generally, the performance level will be B2 in this state, B1 in this state, and B0 in this state. So performability will be the summation of Bj, Pj, performance in this state times the probability of being in this state, plus performance in this state times the probability of being in that state, and so on. So for example, if this is the 2-processor system that I mentioned, let's say performance level is 2 in this state, it is 1 in this state, and it's 0 there, then I can say 2 times P2 plus 1 times P1 is the performability of this system. And there's a numerical example down here that you can study on your own. Okay, so here we model the fail-soft system, assuming that when one of these processors fail, we always go to this degraded mode with one processor. Therefore, we have perfect coverage. In other words, we detect the failure always, and we are able to reconfigure the system so that it continues its operation with one processor. As I mentioned last time, this is not guaranteed to be the case. So if we want to model that situation, we may replace our model with this model. Still, we have high performance state, low performance state, maybe fail state. And then when something fails in the high performance state, with some probability, we succeed in reconfiguring the system and going into this state. So the original rate here was lambda 2. C is a constant less than 1. So if the coverage factor is 99%, 99% of the failure cases lead us to this state, and 1% of the failure cases lead us directly to this failed state. So this is modeling of coverage factor. Again, we can set up the balance equations, and this sum of probabilities being equal to 1, solve the equations, and we find P0, P1, P2 as a function of these various parameters and the coverage factor C. Okay, if we want, we can also define a coverage factor in the repair direction. Perhaps it's not guaranteed that we can successfully repair a failed system. So maybe take C prime to be the coverage factor in that direction. So with probability, with rate C prime times mu2, we go to state 2. With probability 1 minus C prime times mu2, we remain in this state. In other words, we are not successful repairing. And then if we are not successfully repairing, eventually a second failure occurs and takes us to this state. Okay, as you see, the examples are getting more and more complicated, but still we have only 3 states. Potentially we can have many more states in modeling a computer system. Okay, now let me tell you a little bit about how to solve Markov models to find the time-dependent probabilities or transient probabilities, not just the steady state, which are easy to obtain. So I set up the balance equations for this system. The rate of change at state 1, P prime 1t, is negatively correlated with P1t, and is positively correlated with P0t. And then probability of being in state 0 changes. This is the departure probability mu, so it's taken into account with negative sign. and this is the arrival probability lambda. So I have two equations, two differential equations that I need to solve. There are two unknowns, P1 and P0, P1 of t and P0 of t, and two differential equations. You may not have seen this, or you may not have remembered if you have seen it in math courses. So let me explain how these systems of first order linear differential equations, they're linear because the constants are, the coefficients of these terms are all constant, negative lambda, mu, negative mu, lambda. So the variables are P1 of t and P0 of t. These are the derivatives, and the coefficients are constant. How do you solve these? Here is the procedure. To solve linear differential equations with constant coefficients, do the following. Convert the equations to algebraic equations using Laplace transform. So we use Laplace transform to convert these equations into algebraic equations rather than differential equations. Then solve the algebraic equations. We know how to solve a system of two algebraic equations. And then use inverse Laplace transform to find the original solutions. Okay? Laplace transform is defined by a table of functions in time domain and their corresponding functions in the transform domain. The entries in this table are all we need for solving our examples in this course. This table can be larger. If you look at some sources, there are more entries. So what does this table say? It says a constant function in time domain in the transform domain becomes k divided by s. S is just a variable in the transform domain that we solve for eventually and find it. If you have an exponential function e to the minus at, the transform version, so we denote these functions by, in the time domain by lowercase letter, and in the transform domain by uppercase letter. So the function e to the minus at becomes 1 divided by s plus a. Okay? The function k times h of t, in other words, if you multiply some function h of t by k, its transform is also multiplied by k. So you don't need to worry about constants. If you find the transform of h of t, then the transform of k times h of t is just k times h of s. So this h, capital H, is the transform version of this function lowercase h. If you have the sum of two functions, then you can individually find the transforms of these two and add them. Perhaps the most important for our examples here is this. If you have a derivative in the time domain, in the transform domain, so h is a function, big H is the transform version of that function. So it will be s times h of s minus h of 0. This is basically the initial condition. Okay, these will become clear as we apply it to this example. So p prime 1t converted to transform domain, it's of this form. So we will have s times p1 of s minus p1 of 0. S times p1 of s minus p1 of 0. And on the other side, just have, constant multiplied by functions. So minus lambda times p1 of s, the transform version of this function, plus mu times p0 of s. Similarly, for this one, this derivative, I use this correspondence to write it as s p0 of s minus p0 of 0 and then the right-hand side is again simple. And P1 of 0 I know is equal to 1. At time 0, the probability of being in state 1 is 1. And at time 0, the probability of being in state 0 is 0. So those I replace with their values. And then I have the two equations with two unknowns, P1 of S and P0 of S. I solve those equations, and I get these solutions for P1 of S and P0 of S. P1 of S is S plus mu divided by S squared plus lambda plus mu, quantity times S. P0 of S is lambda divided by, in the denominator, S squared plus lambda plus mu, quantity times S. Okay, now I have the solutions in the transform domain. I need to go back. To go back, I basically have to look at this table in the reverse direction. So if I see K over S here, I replace it with K. If I see 1 over S plus A, I replace it with e to the minus AT. Okay? And so on. However, what I see here does not have the form of the functions in this table. So for example, I have S squared in the denominator. Well, this could potentially have S squared if n is equal to 2. But then the other terms will not match. Here I have S squared. If n is equal to 2, I have S squared plus 2as plus a squared. So that doesn't match the form of this function. Okay? So what do I do? The solution eventually we'll see will be this. But let me tell you how you obtain those solutions. So when you have an expression in the transform domain that does not match any of these, then you try to transform it into sum of terms, each of which does appear here. And therefore, because the sum of two functions, the transform of the sum of two functions is the sum of the transforms. So if I convert this into the sum of two things, say of this form, of this form, or of this form, then I can directly write the corresponding time domain functions, and I'm done. So how do I do this? This is done by basically expansion of fractions into simpler fractions. So let me give you just one example. So take this fraction, s plus mu times s squared plus lambda plus mu times s. This s plus mu is a constant, so I can ignore it for now and then reintroduce it later. Okay, remember, a constant times h of s. If I find the time domain version of this, I can just multiply by k to get the time domain of this. So let's ignore this. So okay, sorry, I didn't take that path. I simply multiplied out this. I could have done it that way. Sorry, this is, sorry. This is not constant. It has an s in there. Totally wrong. So I do have to, so I divide s by this fraction. And then when I divide s by that fraction, s and this power and this s cancel out. I get this fraction. And then divide mu by this expression. And this is the second part. Now the first part, notice, is already in the form that we need, is 1 divided by s plus some constant. And we already have a function of that form here. So it will be e to the minus at, but a here is lambda plus mu. So we know the time domain version of this part. What about the second part? Here I'm going to ignore mu because it's a constant and just focus on 1 divided by s squared plus lambda plus mu s. Okay, say this is basically s. I can factor out s. So it's s times what is left is s from this term and lambda plus mu from this term. So I say, okay, this is probably the sum of two fractions, one of which has the denominator s, the other one has the denominator s plus lambda plus mu, because I factored out the denominator as s times s plus lambda plus mu. So there is some number at the numerator, I don't know what it is. There is some number b at this numerator. I don't know, I'm trying to determine what those might be. Okay, so now try to combine these two. When I combine two fractions, I multiply the denominators, s times s plus lambda plus mu. And then I have a times this plus b times this. So a times this denominator plus b times this denominator. And that should be equal to 1. Because I started with this fraction. I decompose it into these two fractions. The sum of these two fractions should equal that. And therefore, this expression should equal to 1. Okay? So that basically means if I factor out the terms that have s in them, I have as plus bs. Okay? I don't have any s on that side, so a plus b must be 0. And then I also have a times lambda plus mu, but because so a plus b should be equal to 0. And then a times lambda plus mu should be equal to 1. And therefore, a plus b 0 and a times lambda plus mu equal to 1 give me the values of a and b. Okay, once I have the a and b, I plug into here. So here I have some a, which is 1 over lambda plus mu divided by s. That's of this form. And here I have b, which is this negative value, divided by s plus lambda plus mu, which is of this form multiplied by some constant. Okay, so I now can go back and find the answers that I gave you on the previous slide at the bottom. So notice here, these are the transient probabilities of P1 and P0. Again, if t is equal to 0, then this term becomes 1, and P1 of t becomes 1, and P0 of t becomes 0. If t is equal to infinity, we get the steady state probabilities. Okay, so that checks out. Okay, so you don't need to become, fluent or conversant with these Laplace transforms. You can always use, reference sources. Sometimes the function you are looking at, you can look up just the Laplace transform directly from the internet, or the inverse transform you can look up. But in the worst case, you have to do this process. And it's doable. You don't have to memorize these because you can always look up the correspondences and work your way through any given problem. Okay, now what I have in this last section of the textbook, chapter 4, are a bunch of examples to just basically provide more exercise, more practice for dealing with these models. So a particular Markov model that is used extensively in practice is the so-called birth and death process. Okay, so the name comes from the fact that if these transitions going rightwards are births and transitions going leftwards are deaths, then starting from a population of 0, you can go to a population of 1 as a result of a birth. Of course, in the case of humans, it doesn't make from population of 0, you can't increase the population. But this is more general than just. I'll give you a good example in a minute. And from a population of 1, you go to 2, up to n. And this can continue up to infinity because the population can increase. And then, so these are the birth rates, and these are the death rates. And then given particular values for these lambda parameters and mu parameters, you can find the probabilities of being in these various states, so the probability that the population is 3 or 4 or 5 and so on. Now, this model, one of its most famous applications is in modeling wait times in banks and other places where customers go to get service. So in this case, 0, 1, 2, 3 can be the length of the line of waiting customers. So suppose there's a bank and there's just one teller that serves all customers. So initially there are no customers waiting. A customer enters. Customers enter at some rate, maybe one customer every 3 minutes or whatever the load of that particular bank branch is. And then the customer is served at a particular rate. So if lambda 0 is 3 minutes, arrival rate is 1 every 3 minutes, and then the service rate is 1 every 2 minutes, then it's less likely for the line of waiting customers to grow. If arrival rate is 3 minutes and service time is 5 minutes, of course the line will grow indefinitely and towards infinity because the rate of service is lower than the rate of customer arrival. Surprisingly, if you solve this model, if the rate of service is slightly less, let's say this is 5, this is 4. You might think if a customer arrives every 5 minutes and the customer is served every 4 minutes, there's no reason for a queue to form, for a line to form. However, remember, these are probabilistic parameters. A customer arrives every 5 minutes on average. Okay? So, 2 customers can come in at exactly the same time or within 1 minute of each other. So the average rate is 5 minutes, one every 5 minutes, but it can be more. The interesting thing is that once the line starts growing, because a few customers arrive close to each other, then the line will not shrink very quickly. Okay? In fact, you can have arbitrarily long line even when the service rate is higher than the arrival rate. So this is one application of this model. Of course, you should know now how to solve this. You set up balance equations. and then you solve the balance equations. I've given the solution here. Pj is P0 times this ratio of the product of lambdas divided by the product of mu's up to that jth. And of course, then if you have all probabilities in terms of P0, then you just set the sum of them equal to 1 to find what the value of P0 is. Okay, I already explained this, written it. Okay, in the previous example, the death rate is constant regardless of what the population is. So in the bank example, the arrival rate of the customers does not depend on how many customers are waiting in line. Okay, the service rate is also constant, but this doesn't have to be the case, and we can just define. So if this is a multiprocessor system with the numbers now indicating how many processors have failed, 0 have failed, 1 have failed, 2 have failed, and so on. So if n processors are operating, then n lambda is the applicable failure rate. If n minus 1 are operating, okay, so you can use this model in that context as well. And then going back for repair, you can put mu on every one of these transitions. If you have a single repair facility, you can put 2 mu on some of these if you have 2 repair facilities. Of course, here it remains mu because there's just one failed processor. Okay, but the other ones can be increased to 2 mu and so on and so forth. Here is a model of a TMR system, triple modular redundant system with repair. So you have 3 operating modules. This is the failure rate for one failing. You have 2 operating modules. Still, you can get the correct answer even though one has failed. But if you have repair so that one failed module can be brought back into service, the lifetime of the system, expected life, will increase. Because if the system is in state 2 and you don't have this repair, eventually it will go into the fail state. When one of these 2 fails, the rate being 2 lambda. But if you have this repair and repair rate is much higher than this failure rate, very likely you bring back the system into full functionality before this occurs. And therefore, the system will fluctuate back and forth between these 2 states many times before the system fails. So you expect that mean time to failure of the system to increase. I let you read the details on this slide and in the textbook. Sure enough, it does. When you have triple modular redundancy, when you have a non-redundant system, the failure rate is lambda, and the mean time to failure is 1 over lambda. Let's say with 10 to the minus 6 per hour, it will be 1 million hours. When you have TMR, surprisingly, the mean time to failure is less. So imagine that this repair transition isn't there. Because of this triple failure rate there and double failure rate there, okay, the mean time to failure is actually reduced. But that's not worrisome because in the short term, reliability will be higher. In the long term, reliability will be lower, but we don't use the system over an extended period of time. When you go to TMR with repair, you can derive the mean time to failure. And I've written it in this form so that it's directly comparable to that. 5 over 6 lambda times this factor. What is this factor? Is 1 plus something, so it's more than 1. Therefore, there's an improvement in mean time to failure. How much more? Well, 1 plus 0.2 times mu over lambda. Remember, we said that mu over lambda is a large number. It can be 10,000, it can be 100,000. So mean time to failure will be improved significantly. In this example, I've taken mu to be 0.1 per hour. It's rather pessimistic, meaning on average it takes 10 hours to do a repair. And it becomes, instead of about 1 million hour, it becomes 16,000 million hours or 16 billion hours. It's really significantly improved. Okay, the dependability modeling process is an iterative process. You choose your modeling approach, whether you want to do the combinational model or state space model. You choose an approach depending on which one fits your needs better. You construct the model. You derive the model parameters. You solve the model. So you solve your Markov model or solve your combinational model. You interpret the results, and then you validate the model and result, and you are done. Unfortunately, most of the time, you just don't go one pass down this path. You may have to go back and adjust things. Okay, so when you try to interpret the results, you see that something is wrong, and then you may have to go back and redo your modeling, redo your derivation of your parameters, and so on. So once you are done once, you sort of may have to go back. And when you go back, you either go back to all the way to the beginning, redo the entire modeling process, or maybe somewhere in between if you know that there's something there that you can fix. My final slide is a list of some software aids for reliability modeling. If you work for a company and you are in need of doing reliability modeling, there are software products that are available and can be purchased. Some of them are pretty expensive. So PTC Windchill is a company that specializes in reliability engineering, and it has a bunch of products, software products you can purchase. University of Virginia and Iowa State universities have their programs, and these are free of charge. You may have to register to get access to those programs, but they don't charge you money for those programs. There are some tools built upon MATLAB. So if you're a MATLAB user, you may want to look into those tools. They're MATLAB based. Again, they can be, they may require purchasing or in some cases be free. That's it. So when I updated the slides, I sort of double checked all these links. In some cases, the links were broken or obsolete. And to the best of my knowledge, these links now work, and you can pursue them to find out more information about these modeling products. Now, for the purpose of this course, we don't actually run programs. We form models on paper. You may do homeworks designing a model and finding its parameters. If you do research in this area, if your research topic is related to this, we don't have any budget to go and buy these products, but we may gain access to these free modeling tools and use them in case your research topic requires that you do actual modeling. But for the most part, you can just put this in the background, know that these exist so that in case you need them in future, you can go and find them and acquire the necessary tools for your work. Okay, so this ends our discussion of Chapter 4, State Space Modeling. and stay safe. I'll see you in lecture 5 next time.